works out. Okay, so let's press on now that everybody is in. We're past machine time. Let's start off with some machine learning tools. So I opened this in a new tab, okay, and that's what it looks. And one very important thing I want to mention to you is that for every one of these web pages that I'm showing you guys, if you take the URL address, and just replace the extension HTML at the end by capital RMD for R Markdown, you're going to get the source code that generated that page itself. So for example, I can, is that right here with what I'm doing? I'm just changing the extent, right? So this is the page that this links to. Look, I'm not sure if you can see this, but this kind of links you to chapter 10 of the book, and the extension is HTML, and then I'm just changing the extension HTML at the end by RMD to get the source code. This is our code that generated the page itself. Is it right here with me? So I can now save that. I can go to File, Save, and I'm going to put it in my folder. Remember, I have already one thing there, so, oh my gosh, sorry. So right up here, you guys, this is the thing that I just, okay, so this is interesting. This is a Macism. This is, Apple think that they know what they're doing. They don't. So they're putting an extra .txt extension at the end of my file, which is totally crazy. So how do I rename that? Correct Apple mistake here. Okay, and now I need to, now for PC users this is going to work smoothly, but for Apple I need to associate this file with our studio, right? Is that right here with me? So how do you do that now here? Okay. Okay, open with our studio. And now look what happens, you guys. Does everybody see this is my file from yesterday that we kind of mocked around with, but I have a new file here, and this is kind of strange, but we didn't really associate. So how do you do this thing right? I think you gotta do open with other. Always open with our studio. Okay, and now it's supposed to change the icon. It's supposed to put the R studio icon there. I'm not sure why. On a PC it should work, right? Anyways, so the point I'm trying to get across is that now you guys, I'm going to be kind of scanning over the website, but you are going to have that window open, and when I go over a piece of code in the HTML, you're going to be finding that piece of code right up. And again, it may be wise here to stretch a little bit this window. Because look, remember how I told you last time that, see how nicely it renders directly in the source code, it renders the math that you've written here in terms of LaTeX, okay? If you don't know LaTeX, don't worry about it. It's a mathematical typesetting software that was invented way back in the 80s. It's how books are typeset. Everything that has special characters, well, most of the modern books and articles are typeset in LaTeX, which is this syntax language. So for example, here is your sum, /sum generates this sum, and then the function f, the parenthesis, left, right, w sub I, x sub I. So it's got this, you don't have to know LaTeX, but it generates in the R Markdown source most of the stuff that you're going to be going over. And then, here is the piece of code, you guys, that, for example, when I go over this, you're going to be just highlighting this and click run. And now, just run the selected, run the currently selected. So Apple enter, I guess, is the shortcut notation for this. So if I do Apple enter, it runs it, but you see when it generates a plot, the plot does not go over here under plots, but if the plot is generated in the code itself. See what I'm saying? If you want the plot to pop out, you need to copy this, paste it down here. Oops, sorry. Oh my gosh. What was it? Function escape? Yeah. Okay, so I need to do, I need to copy this, paste it in there, and then run it, and then the plot is going to be showing up where you expect it to show. Is that right here with me? So a little, it's really clever, it's really nice, it's very elegant, it's well designed, but I just want to show this dichotomy here a little bit. Okay, so, so we have the code, and when you don't want some of this, because it kind of gets on the way of the content, just exit, and then it continues down, okay? So the next segment of code starts over here, and does another plot, okay? This one does another plot. Okay, so what we're going to do now is we're going to start with that section now. Okay, so let's go over this machine learning base 2. So here I may have to zoom out a little bit, or let's see. So let's just go over some of the technique, because we're not going to be able to cover everything start to end completely with all the sections that I want. So let me just tell you what's in this section and kind of see what may resonate with you as to stuff that may be worth going over. So the first thing is we're going to draw some parallels between the biological central nervous system, the brain, and the artificial networks created of artificial neurons. So we're going to have a little bit of this, and then we're going to show various types of activation functions, talk about network topology, and then layers and various things, how to train a neural network with backpropagation. And then we're going to do some case studies. The first one involves Google Trends and the stock market. The next one involves a very simple neural net method that attempts to mimic square root calculations. You know, very simple. Somebody's going to say, why do you need the square root calculations? Well, think about it. If I ask you to compute square root of a number without a machine, what are you going to do about it, right? You've got to think a little bit about it, right? There is algorithms. Kids learn this in 5th grade. I don't remember what the algorithm was, but there is a process. You know, you want that precision, repeat 5 times, you know, whatever. But if I ask you, most of us don't remember how to compute square root. So we're going to train a neural net that learns from a few inputs and outputs of the square root function. It's going to try to find the association, and then we're going to use it to predict some new numbers, right? Just to illustrate something basic, a fundamental principle, taking a square root of a number, right? As an example. And then we're going to talk about support vector machines. And then I want to go into a very interesting case study, optical character recognition. Suppose somebody writes letters, and everywhere I go, I write a phone number on a piece of paper. Nobody can read my handwriting. It's kind of crazy. Most of us, if you write the number 7 or 6 or something, hardly it's going to be recognizable. So machine-based interpretation of handwritten digits or characters is very important, right? So we're going to show an illustration of how this thing works. And then we'll probably skip over this academic example with the iris flowers that I showed you earlier. And then, there is an interesting problem set that we can practice, I guess, if there is interest, quality of life in chronic disease. All right, so, that's actually nice. So why don't we stick with this? So this is kind of large. So this chapter, by the way, parallels some of the work continues in chapter 22 as well, where we talk about deep learning. So the basic idea is that you have signals as inputs, x1, x2, and x3, and what you want to do is you want to have a neuronal cell. You know how neuronal cells work, right? I have a diagram a little bit later, but it's basically a discrete computer that feeds in dendrites from other neurons, and it makes a decision. Either it fires or it doesn't fire. It's a binary process, right? Action potential increases. At some point, it passes a threshold, neuron fires, signal gets sent down its axon, reaches the next cell, it collects input from all kinds of cells, and it acts on it. So the basic idea is that you have these inputs, xi's, they're weight averaged. Okay, weight averaged is what this corresponds to. They have weights, and remember I told you that total sums are equivalent to averages. So I'm referring to this as weight average the input, apply an activation function, and this is what comes out downstream from the neuron. So activation functions, here is one activation function, which is kind of called hard threshold. You stay at 0, no activation until certain threshold is reached, and then you fire up. This is a piecewise linear function. 0 until you reach 0, and then 1 for everything that exceeds it. But you can also have some more interesting function, like the sigmoid activation function, which is 1 over 1 plus e to the minus x, and as x goes to minus infinity, this goes to infinity, and then the function goes down to 0. As x goes to plus infinity, this becomes 0 effectively, because it's 1 over infinity is 0, and 1 over 1 is 1. So this hard threshold function that's very kind of rapid can be smoothed out a little bit to look like this. So that's the graph. That's the graph of this sigmoid function. And by the way, this is exactly what we had right up here that I just plotted a second ago. Does everybody see the definition here? It's exactly the same definition. 1 divided by 1 plus e to the minus x. Okay? And I'm just plotting it here so to show you. Now, look at this little delimiter here. Echo F means that when you generate the HTML page, don't put the code in, because it's kind of irrelevant in this case. Remember, when I look at the material, the code that generated the function is irrelevant, right? So you kind of hide it. Is everybody here with me? Because it has nothing to do with you just want to see, well, what does this function look like? Well, that's what it looks like. It's smoothly transitioned. It's not the rapid change that we saw with the previous hard threshold. And you can have all kinds of things, right? You can have, here is a linear function, saturated linear, hyperbolic tangent. That's an activation function. You can have Gaussians, and you can have all kinds of things. So the network topology, so remember, every one of these nodes here is an artificial neuron. It takes in its x1, x2, x3 inputs. This guy takes 3 inputs. These guys only take 1 input each, and then they generate one output. But this output can be sent several different ways, right? And then ultimately you get an output node. So this is called, the data gets fed in here. The input nodes are on the left. The hidden nodes are over here. And you see, x1, x2, x3, the input data. Remember in the formula out there we had x1, x2, and x3 weight average. Well, the weight averaging happens right up here because for each of these connecting edges, you're going to have a W3, W2, W1 gets fed into each of these hidden. And you can have multiple hidden layers, layer 1, layer 2, layer 3, until you get to the output, and the output is whatever it is, right? So, this is a directed graph. They're typically acyclic, which means that you can't feed back from H2 backwards to here because you're going to end up in an infinite loop. You never come out of it. Although in reality for biological systems, you can have a feedback loop, right? For instance, as you get sensory visual input, your network constantly processes, right? You got to go in the loop, and you're kind of looking at, is the number A there? You're kind of focused, and you kind of constantly monitor the situation until you find the letter A, and then you take action, press a button or something like that. But for artificial neurons, these are typically, acyclic. Now, there could be delays factored in these things, so they don't fire at the same time. There's various complexities that can be put into place. Okay. So let's look at one simple example first. The Google Trends and Stock Market data set available right up here between the years 2005 and 2011. And here is the metadata if anybody wants to get. Here is the exact download of the data. It's available on our case studies site. So here is what it basically has. Index of an observation date, unemployment rate, rental index that kind of captures, how expensive is the rental, mortgage index that track, mortgages are when you buy a house, you typically take a loan, which is referred to as a mortgage, and then you pay it over a number of years. The bank pays for the house, you owe the bank, and then it has a job index that tracks queries related to employment, investment index, etc. Dow Jones Industrial is one of the international indices, stock market indices. A version of it is called the standardized Dow Jones. And a 30-day and 180-day moving average of the data. So what we can do is, again, so right up here, if I do, you can copy this with a mouse, go back to the source code, and here, you guys, if I do find Control F and paste that, it's going to get me right in the code. That's strange. On a Mac, it doesn't show you. On a PC, it shows you here, roughly speaking, where are you in, because it's a long file, right? I'm on line 152, when in fact there is thousands of lines. But it should show you on a PC here exactly where you are relative to. So this is, so you guys may want to kind of run this thing, get the data. Again, for me, Apple return or Control Enter on a PC. You see how it tells me it's retrieving the data right now? So it's green and the stop sign, now it's done. So I should have here in my environment of variables this new object that just popped in, right? So I've got this new object that I can now process. And then look at what happens up here now. So in these two lines, what I'm basically doing is I'm taking, remember this is a two-dimensional array, a matrix with rows and columns. I'm taking all the rows, all the records, but I'm removing columns 1 and 2 because, let me just see, do I want to do that? Okay, I just removed them because they had some indexing, some irrelevant stuff. It has nothing to do with the actual data. So now you end up having a data frame that has 731 observations. These are your rows, and 24 features, and these are your variables. Okay? And again, you have the result here. I'm going to X that. All right? And then what we're going to do is we're going to define a normalized function. So what this function does is, here, it essentially transforms every vector, every feature, every variable by subtracting away its mean and dividing by the range. Max minus mean is the range. So when you do that, all of your results that get returned by the normalized function are always going to be between 0 and 1. Does everybody see why? Because every value is always bigger than the mean, but less than the max. So the maximum the numerator can be is max minus min, which is equal to the denominator. So you got a maximum of 1 and a minimum of when these two are equal, and that's going to be 0. So now all of your values get transformed from 0 to 1. And sometimes this is useful, especially in the case where you have one feature, like for example, for those of you that know, are familiar with cognitive scores, the Mini-Mental State Exam Score, MMSE, is a measure of cognitive ability that goes between 30, 20, 29 and 30 are normal cognitive abilities, and as it goes down to 25, 22, 20, and then below 20, this is a strong indication of cognitive disability. So, for instance, dementia. Okay? So, the Mini-Mental State Exam scores, there is all kinds of things. So, if this is on the range from 0 to 30, these scores, where 30 is normal, and as you progress down to below 20, cognitively abnormal individuals. Some other tests, for example, might have values that are in the thousands or tens of thousands. Okay? And when you do the weight averaging, remember, you're doing weight averaging, which means that the values that are bigger are naturally going to have a bigger impact on the decision making in this neuron. So to take away the scale of each feature, you're essentially normalizing, because this result here has no measuring unit. It's called a unitless quantity. It doesn't have a measure of meters, frequencies, time, interval. You know, it's unitless. It doesn't have a measuring unit, right? And that's why when you start weight averaging these things, it makes sense what you want. Because when you go to the grocery store and you want to buy a pound of apples and a pound of oranges, you don't put them in the same bag and they don't measure them together, right? They split them because they have different prices, right? Okay? That's exactly what's happening with this normalization function. It's a very important one. And then, you see, this is a little clever one-liner that applies that normalization to the entire data set. So, it takes the Google data set and L applies the normalized function to every one of its columns or features and saves this as a data frame. And now we're going to have this, we're going to label this Google_norm for normalized, and then we're going to print a summary just of the one of the features, the real estate index, remember? And it kind of shows you that indeed the minimum is 0, the maximum is 1, just to validate that our normalization kind of works. Now, that's not the only normalization you can do. Everybody's probably familiar with the standardization formula, remember? Where you have a value, subtract away the mean of the feature and divide by the standard deviation, right? This is called the standardization formula, okay? Which essentially transforms most of the variables. It makes them look like Gaussian, even though they're not, but it kind of makes them symmetric around 0 because you subtracted away the mean, okay? And then because it corrects for the standard deviation, these are also unitless quantities, because on the top you have the same measuring unit, the standard deviation is measured in the same units, so the units cancel out, and the standardization or the normalization are both unitless measures, right? Okay, so, and by the way, in R this is very easy. I could have set here scale. Let me just do this real quick. So if I do change here this to scale, see how it suggests for me? It tells me right away that scale is a generic function, blah, blah, blah. You can press F1 if you want to have additional information here. Is it function F1? Yeah, function F1, and it kind of shows you right up here. I just press function F1 to get the full description of this function here in my help tab. And then, you know, if I rerun this and rerun the summary again, now you see I have something, mean of 0 makes sense. Standard deviation, well, I can probably compute the standard deviation of this, but the minimum is minus 2.7. That's okay. So it's not quite symmetric, mind you. It's not quite symmetric, but I can probably do a histogram of this as well, just to show you that it should look somewhat. It should look somewhat reasonable. Copy, paste, paste, enter. So, as I said, it's not very symmetric. It's not really Gaussian, but it's again unitless, and all the values now, not only the real estate index, the stock market index, all the searches that came with the Google dataset, they're all kind of going to be similarly scaled. Okay, so and I can do here undo if I want to go back to be able to reproduce exactly what was done. Okay, so press it on. Maybe we should go over here. Okay. So we standardized. Okay, so now what we're going to do, you see, this is off. I don't know why. Oh, battery is empty. Okay, can you guys hear me in the back? Okay, all right. So now we got the data in. We got the data pre-processed a little bit, gently massaged a little bit, okay? Everybody likes a massage, even the data. So what we're going to do now is we are going to randomly split the data into a training set that we use to learn the affinities from, and a testing data set that we're going to leave aside for validation purposes at the end. That's the goal. So that's exactly what's happening here. 75% of the data, we're going to use the majority of the data to learn from, and then the minority for validating our learning process. It's just like, in school, you spend most of your time learning, and then they put you on a test, you take the test. That's what we're doing here. Now, look what's happening. How efficient R is in doing all these calculations. If you have to write this from scratch in C, JavaScript, Java, whatever language, it's going to take you thousands of lines probably. So in R, everything is very easy. So what's happening now here is get the number of rows, n row gets you the number of rows, the number of cases we have in a data set, and multiply this by 0.75 and take the floor function, because this times a floating point, this is a floating point number. It's not a specific thing. When I take the floor of it, I take the integer part of this. So I'm randomly sampling 75% of the cases, okay? And I'm letting these be the sub-indices that I'm just letting these be the sub-indices, and then I'm going to construct a new object that Google train that's going to only include the normalized data that has the rows, remember rows and columns, all the columns, but only the rows that correspond to these 75% randomly sampled lines. It's very important that you don't pick the first 75% and then keep the last 25% for training, because maybe the last ones that came, there was a natural trend with time, okay? So you want to kind of randomly choose these things, 75% for training, and then for the testing or validation, we're going to use everything but these. So minus the sub-index array. So you see how efficient and elegant this is? Now it takes a little bit of getting used to it. Yeah.
The sub-variable is just a set of indices that
Yeah.
are randomly sorted from that column.
Not from the column. The set of indices of the rows.
Yes.
Yeah.
Oh, sorry. Yeah.
Yeah.
But it's all the data that.
Yeah. All the data, exactly. All the data, except that from all the rows, you're going to take 75% of them randomly. The sample function is randomly selecting the indices, okay? And then now we split the data. Now the data is partitioned. There is no overlap between training and testing, right? I'm not going to validate on anything that I learned on, right? Okay? Okay, so now we are ready now to start with the learning process. Training a model on the data, and model is not the right word here, but it kind of makes sense because there's a huge difference. These machine learning techniques are called model-free because you don't have an a priori model whose coefficients you're estimating the way you do with linear models. Okay, so we're going to start the learning now, and we're going to use the neural net function in the package neural net. So it's going to return to us an NN object, neural net object, with some of these features in it. So this is how you call it. You essentially give some kind of a response and some kind of predictors functions. You provide the data, and then you say how many of these hidden layers. Remember the little diagram of the topology of the neural nets that we have? I'm just going to keep it simple for now, just single layer. And again, target is the variable that you want to predict. The predictors are the features that you want to use to explain that. And that's what's happening. So I'm going to load in the machine learning neural net library. And here is my code. Suppose I want to predict the real estate index. Why not? In terms of what's the unemployment, what are the rental conditions. Now obviously remember you guys, there is a really nice parallels between rental and mortgages. If rental costs tend to increase, if it gets more expensive to rent, what do you think is happening with the mortgage market? If things get more expensive to rent, people are going to bail out. They would say, why am I putting that much money a month? And at some point, the amount of rent you pay may be equivalent to the amount of monthly mortgage payments that you make, right? So if the rate of the rentals increases, typically the mortgage rates increases as well. And so there is nice, relations. The jobs, I already told you, if the job market is getting bad, nobody's buying. Investment, that obviously isn't predictive, etc., etc. And then you specify that you're only learning on the training data, right? Okay? And then at the end, you're just going to plot the model. And now look what's happening here. Now that may be hard to show on one slide, but it goes in, fits in these models, and computes the weight factors. Remember how the amount of rental information gets doubled. The amount of what's above it, unemployment acts as a negative. Unemployment acts as a negative when you're trying to predict the real estate index. Mortgages, a half, whatever. So these things get computed here, okay? And that's the topology of the network. It reports for you how many steps it went through and what is the error rate. And now what you want to do is, now that you have the model in this object that we call Google model, okay? What we want to do now is we want to assess how well does it perform on the testing data. So right up here, we're going to use the compute. We're going to provide a model, and then we're going to provide the Google test data. Okay, but we're only going to. So you see, we only train the model on these features. Okay, so these are only the features that I need to provide when I call the validation with the testing data. So there is 2 plus 5 is 7. 1, 2, 3, 4, 5, 6, 7. So these are the features that we're calling. And then once you have the predictions, then I can call the neural net result, neural net.result, to get the predicted results. And then what I'm going to do is, because for these training data you do have the real estate values, I'm going to compute the correlation of the predicted real estate indices and the on the test data and the real test data real estate indices, right? So find the correlation between the real training data values and the predicted results. And this correlation ends up being almost 1. What does this tell you? Right, it tells you that it learned really well the relation between these 7 features and the outcome variable and predicted it fairly accurately. It's not perfect. We could have also done plot of these. We can have done a scatter plot. If I replace correlation by plot of this versus this, it's going to kind of show you a paired, and they should be pretty tightly linearly related. Yeah.
Now we haven't cross-validated, right?
We haven't cross-validated yet. Yeah, we're going to talk about that later. Okay. So what he's referring to is that how do we know that, this is just one run through the system. How do we know that this highly predictive value is sustainable? Maybe the way that we chose the 25% to test on, there was something special, whatever. So in the cross-validation world, to which we're going to get into a little bit later, what we're going to do is we're going to repeat this process multiple times, where we sample and resample multiple times, refit the model, and then at the end we're going to be reporting the average of these correlations in a multi-resampling fashion, so that we convince ourselves that what we're doing is kind of stable. So we're going to get to this later. Okay, so can this model be improved? Well, let's change the hidden layers to 4. And now in this case, you see the network gets a little bit more complicated, as you can imagine. The error went down to 0.337, and here it was 0.6. Now, this is error, however, this is the error on the training set itself, which is kind of irrelevant to you. You don't want anything to do with the, well, I mean, it kind of tells me that the next model is slightly better, possibly, but you can't really trust that this error, being smaller is much better than the previous one, because this is on the training itself. And now if you do the calculation, your correlation coefficient went up a couple percentage points. It was so good to begin with, I'm not sure it was worth it having extra layers. The first model, as far as I'm concerned, does a pretty good job. So, okay, so let's go ahead now and do this little example with the square root function. The square root function is only defined, remember, for non-negative integers, including 0. If you want to talk about real numbers. If you want to talk about complex numbers, square root of -5 is perfectly well defined. What's square root of -5? Square root of -5, what is it? Come on, the engineers, square root of -5. It's I times square root of 5, right? So it's a complex number. It's well defined, but let's kind of keep it simple here. So we're going to look at this function. So what we're going to do is to keep it simple, to keep it well organized. What we're going to do is we're going to generate 1,000 random uniform numbers between 0 and 100. It doesn't really matter what. You control how far you want to learn on. Now remember, with learning, just like with everything else, right? If they teach you how to drive a car and then they put you in a tractor trailer, you're not going to know, 24 gears, who's going to shift this? It's crazy. So you learn and you get tested on what you learn, not on what you might have been trained. You know what I'm saying? So it's the same thing. So if your intent is to have a square root function compute really well, the numbers between 1 and a million or whatever, that's where you got to train. I'm kind of keeping it simple here. 0 to 100 is where I want to train. Maybe I want to do a more efficient calculator for square root function. Or for pth root, for example. Could be third root, fifth root, seventh root. And I'm going to learn on 1,000 of these. I'm just going to make sure that, that's kind of repeat. Absolute value, they're all positive to begin with. I didn't need that. But at any rate, so this is going to be my random data. If you're using normal 0, 1, then your observations are certainly going to be negative and you've got to take the absolute value. And then what I'm going to do, you see, is I'm going to construct a data frame that has 2 components, 2 columns in it. The raw data is going to be the first column, and the second column is going to be the square root data, which is square root of the raw data, right? So if the number was 50 here, square root of 50 is what's going to get plugged in here. So 50, square root of 50. 30, square root of 30. Is everybody here with me? So I'm constructing a data frame that has 2 columns in it. And then let's go ahead and plot that. Well, that's what it looks like. Square root of 80, whatever. 88, 9, whatever. Square root of 100, obviously, is 10. Okay? So square root of root is an increasing, monotonically increasing, but kind of like this, right? Not like that. And log function would be kind of like this, very, very much slower increase. Okay, so let's go ahead and learn on these 1,000 randomly selected uniform numbers between 0 and 100. Okay. So I'm calling so here's my model. Net square root is going to be called the name of the model. I am saying that I'm going to be predicting the second column from the first column. And I'm providing the data frame that I created. And suppose I want to work with 10 hidden layers, and this threshold kind of tells me a little bit about the specifications. And now, in the next step, we're going to create a testing data set, you guys. Let's go ahead and create a testing data set that has, that has values between 0 and 200. Values between 0 and 200. So I'm having some of the data is within the range that we trained on, and some of the data is going to be out of the range that we trained on. Is that right here with me? Up to 100 we trained on, between 1 and 200 we didn't. Okay? And I'm going to take a sequence between 0 and 200 at a step of 0.1. So how many observations have I got here? Obviously 10 times 200, about 2,000 testing data is what we're going to be using. Let's do the prediction now. Compute using this neural net model, the testing data, and get the results. And then here's where we're going to be doing the plot of the predicted square roots and the test data square roots, that are the real ones. And you see, this is a plot that plots only up to 12. So I limited here the scope just to show you that there is a fairly good agreement, I guess, except that as you approach the limits, and here, the model is going to be, let me see, this is the predicted, is the actual line, and then the predicted versus the This is the predicted square root. This is the actual square root. So the predicted was a little bit higher towards the in that range over here. Okay? So, well, it is what it is. In the middle, it kind of acted okay, but as you go out of scope, it does digress a little bit. And here is another plot that kind of shows the test data versus the predicted square root of the test data. Okay, again, the lines kind of, you know, digress a little bit between 100 and 200. You guys, can you see how you're kind of slightly off? Because again, you're testing somebody to drive an 18-wheeler tractor trailer when they will learn to have a passenger vehicle license. So it's a bit tricky here. Okay, so let me skip over to the next example. Yeah.
May I ask you a question?
Yeah.
So, like, I know these neural nets are kind of like complex and it's sort of like black box. We don't know what's going on and stuff like that. So, what would you think would be the best way to think about them? Like all those weights that we got at the end of the calculation, are they correlations? Are they?
Well, you know, you can almost think of them as being the way a linear model has the coefficients, which are called the effect sizes. Remember, if y and x are related by a linear model, so y is equal to ax plus b, the a, the coefficient of x, tells you for a 1 unit change of x, what is the corresponding impact on the y. And it's the same thing here with one exception though, because it's not one x, it's multiple x's, but you roughly speaking know, just like we had, remember some signs were negative, for example, and some were positive, it means that they're kind of inversely related. If one goes up, the other one goes down. So it kind of tells you a little bit about the impact, but it's always relative to the entire data set. So it can be interpreted in isolation. It needs to be contextualized a little bit.
So does that also mean that some nonlinear sort of like real world phenomena might not be modeled so we can?
I don't know. So if you have multiple layers, okay, so the question is, remember how the activation function is really dependent upon a linear combination of the inputs? Linear combination of the inputs. Well, square root of 2 is not a linear function. Okay? So the question is, what happens? How does the learning machine represent these nonlinear relations using linear terms? Right? And the answer is, when you have multiple layers, these things kind of are intended to be sorted out. Because remember, everybody knows about Taylor series, right? If you have a complex function like the sine of x function, oscillatory function, nice function, but you always have, you know, if you want to interpolate sine of x, you know the formula, right? It's x, it's, what is it? X minus x cubed over 6 plus x to the 5th over 5 factorial. You know, there's a Taylor series expansion. So it's a nonlinear function, but you control how accurate and how deep the network depth is to learn some of these nonlinear associations. So, you know, so one of the layers may be learning the real linear component, the next may be learning the quadratic component, the next one may be learning the third order component. So, you know, it's supposed to adapt, I guess. So if you have a large set that you learn on, it should adjust to that. And it doesn't have to necessarily correspond to first, second, third order and all that business, but captures the higher order non-linearities are typically captured in later layers.
So how is that different from, let's say, for example, I mean, Fourier says that any kind of function can express in terms of
Yeah.
functions and stuff like that. So how is that different from why don't we use like kind of like Taylor series to model this type of model instead of using the rotary angles?
Right, we can. So the question is, what's the relation between the Fourier representation? Okay, so let's take a step back here for a second. This is an interesting discussion. It's deep discussion, okay, if you think about that. So, on the fundamental level, on the fundamental axiomatic level, you guys, it's well understood that if you have a space X of objects, in mathematical terms, people define the dual space as the space of linear transformations on that space. And the double dual, on an extra level, is the linear transformations on the linear transformations themselves. Okay, so hear me out. I know this is a little abstract, but listen to this. So you've got a space, no matter what it is. You have to have some arithmetic on this space. You construct the mathematical dual, which has all the linear functions, and then you construct the double dual, which acts on this space as set of linear functions on these guys. Okay? Turns out, believe it or not, the double dual and the space are isomorphic, the original space. So this kind of tells you that on a very fundamental axiomatic level, there are dichotomies intrinsic in nature. Okay? And one of these dichotomies is exactly the notion of the Taylor series and Fourier representations. They're the two dichotomies of how stuff gets represented. Let me just give you one example. Every function that has a finite Taylor series representation. So, in other words, think about a function that has a finite polynomial representation. From the constant term, x term, linear term, x squared term, quadratic term, up to x to the kth power term. That's a finite polynomial expansion. Every function that has a finite polynomial representation has an infinite representation in the Fourier domain, which means that when you represent in the frequency space, that very same function, it's going to require infinitely many Fourier coefficients. Now, if you take one of those functions over there in the Fourier domain that has a finite frequency representation and you pull it back into the time domain, it's guaranteed to have infinite representation. So what does this? This tells you that simple things in polynomial space, simple things, the function x, has a very complicated expansion in the Fourier domain in terms of trigonometric functions, and vice versa. The function sine of x, which is very simple in the Fourier domain, it's one term. When you pull it back in the polynomial, it's going to have an infinite expansion. Okay? So this dichotomy kind of tells you that, the base function representation of objects, which are the building blocks of stuff, right? How do you build something? Well, we build buildings by putting bricks down, brick after brick after brick. Well, these are the building blocks. So these building blocks that we use to represent objects are very important, but they're not uniquely defined. There is, for example, a wavelet basis, okay, where the representation functions are not polynomials or sine functions. They're actually fractal waves, okay? And in this space, something else happens. So the question was, why do we need these machine learning? Why can't we just use the standard either polynomial models or the standard frequency models or wavelet? And the answer is yes, you can. The essence, I guess, the essence of the whole thing is which of those representations gives you the simplest, most efficient way to compute the representation, number one, and number two, the most efficient way to interpret the representation. Is that right here with me? So, in the polynomial series, right, take the function sine of x. Sine of x has infinitely many. If I want to have it accurately described, I need infinitely many terms, complex. Now, it's got a very nice representation. Mathematically, we worked out all the details. But inferentially, it's complicated because it requires millions of terms to get it precisely done. And with these machine learning methods, they kind of go in and they say, forget about the basis. The basis of representation is model specific, they argue. In the previous examples with the Fourier and the time representation, they are canonical representations. Canonical means no matter what process you study, it's always the same building blocks. Canonical. In the machine learning, it goes in blinded and it says, well, forget about this, forget about that, let me just look what's in there. And it tries to find patterns, affinities, and self-similarities within the data that can be used as the building blocks. But remember, that's the pitfall exactly at the same time, because when a new data comes in, it has learned the building blocks on a different data set, so they may not match too well. So it's a trade-off, right? It's a bit of a... but these two things are important. How efficient is the calculation of the representation, and how meaningful or efficient the interpretation of the corresponding representation. So that's a good question. Okay, so let's press on perhaps here. So support vector machines, here's the basic idea. You basically use hyperplanes, which can be linear or non-linear, to separate the data. Linear versus Gaussian. There's a little bit of the math. Let's not worry too much about the math now. I just want to go directly down to one example because support vector machines are interesting. So let's look at this optical character recognition task. So we are going to be looking at these things that kind of look like this, you guys. Manually written script characters. Okay? Now, for each of these characters, we've gone through and we've recorded a bunch of characteristics, derived imaging characteristics. So, for example, what's the extent of the height? What's the extent of the width? And then you have these, where does it start? And various other things about these data. So here is some K's, S's, you know. This is just example of some of these data sets. So the data is available right up here. And again, if you look at it, it has these X box location, Y box location, width and height measures, you know, and variety of other metrics. So you don't look at the raw images, because these characters, when they're written, you essentially grid the page. You impose a grid on the page, and I don't know how many of you have tried this, but in PDF, if you open Adobe PDF Reader or Acrobat, it has a function called optical character recognition. For scanned documents, you know, you put something on the Xerox, you copy it, it's essentially an image. So how does Adobe do the character recognition? It does exactly the same thing. It grids the page, and it kind of, the first thing that it tries is it kind of orients it a little bit, you know, because when you put the thing on the copier, you kind of slant it, you know, whatever, it looks funky, right? But Adobe is smart, they kind of register it a little bit, and then they put a grid on it, and they do exactly that. They extract these metrics, y-edge, y-edge X, you know, and these are described over here. If you go to the website, you can find most of these descriptions right up here. Okay, and it's got 20,000 letters. Okay, these are different fonts. So after we read the data in, we're gonna divide it. And now, in this case, because it's all random, this isn't not the best way to do it, but let's just go with the flow. Keep it simple, you know. The first 15,000 of the 20,000 rows, remember, 20,000 instances, and then for each of them you've got these features, okay? And then we're going to keep the last 5,000 for validation. You know, we should have done this with random sampling the way I showed you earlier, but let's keep it now static for simplicity. Now let's go ahead and keep and train support vector machine model here. The radial basis, you can use a different kernel, Gaussian or hyperbolic tangent kernel or various kernels. The kernel lab package is the one that you need. And then KSVM is the function. You essentially want to predict the letter from this notation here says you want to predict the letter. Remember, for all of these 20,000, at the end, one of the columns has the actual label of it. So that's the letter. Use all this tilde dot means use all the features to predict the letter, and the data is the training that we just did earlier. And the kernel is vanilla dot. It doesn't matter what kernel you use now. So the classifier is going to have the object for this. And again, it used 6600 support vectors to split the data. Some of these are training error. This doesn't make sense because unless you redo the model somehow and you get a reduction or expansion of the error, it's a relative error. It cannot be interpreted by itself. And now here's what we're calling the predict function, using the model that we learned, but testing it with the validation data. And we're going to call these predictions. And we're just going to, if you just print ahead the first few things, these are the letters that it reports. These are the 6 letters that it reports. C, U, K, whatever. We don't know what the 15,000 and the first up to the 15,006th character arrays were, but this is what it predicted the corresponding levels were. And now here is, because remember, in this case, you've got 26 different outcomes. It's a categorical label. So you can't really say, it's not a binary classification. Now this table here kind of shows you the relative testing data true letters versus the testing data predictions. And you see A's, so these are the true labels. I only printed the first, oh no, they actually appear below. You see after L, they're wrapped around and appear down here somewhere. So 191 of these A's were captured, but one A was predicted, which in fact was a C, and one A was predicted that was actually a J. Is everybody here with me? The next one, the B's, majority, but 9 D's were classified as a B, and a couple of E's were classified as an E. So, it does make mistakes, but generally speaking, they're loaded right here on the main diagonal, which kind of tells you that this simple classifier works well. Again, not really looking at the images themselves, but looking at these characteristics, the derived characteristics of the grid images in this case. All right, so and the Z is right up here. For example, a J was predicted for a Z and whatnot, but the majority again are down here. Okay, now you may want to say, okay, well, in totality, what was the agreement? So look at this, the agreement is something that's going to be whether or not a Boolean of whether or not they're equal. The predictions on the left and the actual letters on the right are, this double equal means are they equal? It's a comparison that generates a Boolean, either true or false. So out of the 5,000 letters that we saved for validation, 400, so this is what? This is about 84% were correct, and the remaining 16% were incorrectly labeled in totality, right? Which is not too bad. And in fact, if any one of you have actually done the Adobe optical character recognition, it's not always right. It puts bangs sometimes, it scrambles, it doesn't always work right. But at 84%, it's not too bad. You can certainly get this up to 90, maybe even 95% if you train a little bit better, if you do the cross-validation, play with the parameters of the SVM, or use an alternative classifier as well. All right, so here's my 84%. Oh, by the way, so table and prob table. So table and prob.table, probability table simply divides them obviously by the total sum. Divides each value by the total sum.